So now that we've reviewed the definitions of acids and bases, now we can talk about their strengths. So when you have a strong acid or a strong base, what that means is that that species is able to practically fully ionize. In other words, it is a strong electrolyte. So if we have an example, hydrochloric acid, right, this would be an acid based on the two definitions that we discussed earlier. And this fully ionizes, right? So I'm going to use that unidirectional arrow to indicate that it is fully ionizing and only proceeding in that direction to form the hydrogen ion and the chlorine ion. Then in that case, we are going to state that hydrochloric acid is a strong acid because it fully ionizes. In other words, you're going to get an entire breaking up of that initial compound. Same goes for strong bases. Generally speaking, that's going to include a hydroxide ion. However, if you remember the definition, the Bronsted-Lowry definition of a base, you're going to realize that not necessarily all bases will have that hydroxide ion. Therefore, they will not be strong electrolytes under that definition. Therefore, a weak acid or a weak base is going to be a species that is a weak electrolyte. In other words, only a small percentage of those acid or base molecules will ionize. In this case, we will represent them with a double arrow. This indicates that the reaction proceeds in both directions. Therefore, you will not end up with as much hydrogen or as much hydroxide as you would if the reaction were to only occur in one direction. So for an example here, we have hydrochloric acid, a pictorial representation of what we talked about in the previous slide. Notice, when we are introducing hydrochloric acid into the solution, we end up with no hydrochloric acid compounds in the solution. We only have hydronium and the chloride ion. The same goes for the representation on the right-hand side. Therefore, the concentration of a strong acid will be equivalent or practically equivalent to the concentration of hydrogen ions in solution or hydronium ions. Why? Because we will end up with a 1-to-1 ratio. Remember, our equation is going to be the acid dissociates to form the hydrogen ion and the anion, right? So if we have a full dissociation or practically full dissociation, then we should end up with a 1-to-1 ratio between these two species. Therefore, you can assume that when you introduce a strong acid into a solution, its concentration of hydrogen or hydronium will be equivalent to the initial concentration of that acid. And here's a list of some strong acids that therefore will practically fully ionize in solution. They're not that difficult to remember because you really have two groups, right? We have our binary acids and we have our ternary oxyacids, right? So our binary acids are primarily going to be our halogens, right? We have HCl, we have HBr, and we have HI. And we don't have very many ternary oxyacids. The few we have are sulfuric acid, which is something that I'm pretty sure you have come into contact with, hopefully in theory. It is a diprotic acid, right? So protic means proton, di means two. So this is going to be one of our main acids that have two hydrogen atoms. We have perchloric acid, which is going to involve hydrogen bound to a chlorate anion. And we have nitric acid. If you remember your chemical nomenclature, it comes from 8. So therefore, nitric acid is going to be a combination of hydrogen and the nitrate ion. So again, reviewing weak acids, they're going to be acids, right? They're still acids and they still ionize. However, they are acids that only donate a small fraction of their hydrogen ions. In other words, they don't fully ionize. If a species does not fully ionize, you are not going to end up with a 1-to-1 ratio between the products and the reactants, right? So remember, if we're using HF, we're going to have the same formula However, in this case, these species will not be equivalent because HF does not fully ionize. Specifically, the concentration of hydrogen ions in solution will always be much less than the initial concentration of that acid. And we can see that in the pictorial representation below, where we actually see the initial acid species in solution, whereas when we were dealing with hydrochloric acid, which is a strong acid, we did not see any species. Now, remember, strong acids, you will still end up with some compounds that don't fully ionize. However, the majority of them will break up and ionize. Weak acids, however, they will not. In fact, you have much less than 1% ionized or ionization of that species in water. These are some examples of weak acids. A great way to remember them is that if it's not a strong acid, it's a weak acid. So if the strength of an acid or a base is dependent on their ionization, well, ionization has to do with the attraction between the anion and the hydrogen ion. In other words, if we have a very strong attraction between those species, then the compound is going to be less likely to ionize than if that attraction is weaker. Again, it all goes back to those interactions. Acid or base strength is therefore, because remember, we're always dealing with equilibriums in these types of scenarios. It is therefore going to be measured using the equilibrium constant of a substance reaction with water. So the first step we will take in determining the acid or base strength is we're going to take that acid or take that base, combine it with water, and determine the equilibrium constant of that equilibrium reaction. When you have that equilibrium reaction, you can therefore solve for the equilibrium constant expression. This will help you solve for K. The smaller that K value is, the weaker the acid or base will be. That indicates the directionality of that equilibrium, right? Because the position of equilibrium depends on the strength of attraction between the base form and the hydrogen ion. Stronger attraction means stronger base or weaker acid. And here's a pictorial representation of what we just discussed. Notice we have a strong acid. In the strong acid, we have weak attraction and complete ionization. Why? Because in order to fully dissociate, a species must be weakly attracted to one another. When they're weakly attracted to one another, then they're going to very easily give in to the effects that the solution has on breaking them apart. Weak acid, on the other hand, we're going to have strong attraction between, and remember, when we're talking about an attraction, we're talking about the attraction between the anion and the cation. In this case, our cation we're going to be representing as hydrogen. Our anion can be anything, right? So in a strong acid, it's probably going to be something like chlorine. In the weak acid, it's probably going to be something like fluorine. So specifically speaking about the acid ionization constant, remember, it's the equilibrium constant expression of the reaction, or basically of the dissociation of an acid, right? So if you want to determine the strength of an acid, you have to write out the equilibrium equation of its dissociation, right? And that has two variants that we have here. The first variant is we combine it with water. What does that do? That basically grasps the hydrogen ion and combines it with the water molecule to give us hydronium. If we are not going to be including water, then all we do is we have hydrogen as an independent species. Either way will give you an equilibrium constant expression that you can use to solve for the equilibrium constant, which in this case is called Ka, or the acid ionization constant. Why do we call it an acid ionization constant? Because in order to measure the strength of an acid, we have to measure its dissociation or its ionization in a solution. The larger the Ka, the stronger the acid. Why would that be? Well, stronger acid means that we have more hydrogen in solution, right? So therefore, if the numerator increases, Ka will increase. Therefore, Higher Ka indicates higher concentration of hydrogen, which indicates what? Indicates stronger acid. And these are going to be this is going to be a list. Again, the majority of this information does not have to be memorized. These definitely do not have to be memorized, right? If you're given the chemical formula of an acid, you should be able to very quickly determine its ionization reaction, because all that is taking that acid, abstracting a hydrogen ion from it, and leaving the anion as its own species. There's two ways you can write this. You can write it with H2O and you can write it without H2O. Keep in mind the difference that makes. If you include water in your equation, you cannot have a hydrogen ion on the product side. You have to have hydronium ion on the product side. If, however, you choose to not include water, you are free to keep hydrogen as its own species. This also includes our Ka values. These are not values you will have to memorize. If you need them, you will be provided with them. So now we're going to talk about the autoionization of water. So we've already talked about water. Water is really an important concept in really any chemistry course you take. So we've already talked about the amphiprotic or amphoteric nature of water. Remember what that means? That means that water can either act as a base or acid. But water also undergoes an autoionization. So what that means is that water can react with itself. Why? Because remember, water can act as an acid and a base. Therefore, under that notion, one water molecule can theoretically donate one of its hydrogen atoms to another water molecule, making that other water molecule a base and making the initial water molecule an acid. Why? Because a molecule that donates a proton under the Bronsted-Lowry definition of an acid is considered to be an acid, and a molecule that accepts that proton is going to be considered a base. You can also write that chemical equation without the presence of water, right, or without the presence of that solution as the following. All aqueous solutions contain both hydronium and hydroxide. Why? Because all solutions contain water, right, specifically aqueous. Right? Very important. You can have solutions that don't have water in them. However, if you have an aqueous solution, that means you do have water, and since water autoionizes, that means you will always have hydronium and hydroxide. Now, you may think to yourself and wonder why you can drink water if it has a potential for having all of this hydronium and hydroxide. Well, the concentration of hydronium and hydroxide will always be equal in pure water. Therefore, remember, acids neutralize bases, bases neutralize acids. So since you have an equal concentration of hydronium and hydroxide in pure water, they will not affect you. They will not vary the pH by much because they are neutralizing one another. This concentration, again, in pure water is going to be 10 to the negative 7th molarity at 25 degrees Celsius. This represents the concentration of hydronium in pure water, as well as the hydroxide ion in pure water. Now again, the product of these two concentrations is always going to be that same number, right? It's always going to be 10 to the negative 7th. The number is called the ion product of water and has the symbol Kw. So again, we've talked about K before. K in general means constant, right? That's the definition of K. Ka is going to be our acid ionization or dissociation constant. Therefore, Kw is going to be the water dissociation constant or water ionization constant. So therefore, remember, so how do we come across, or how do we solve for a equilibrium constant expression? Well, we take the products, the concentration of the products, and we divide them by the concentration of the reactants, right? So if we take the concentration of products in the water equation that we had earlier, so this is going to be the equation we had earlier, right? The autoionization of water. Now remember, what do we include and what do we not include in an equilibrium constant expression? We will always include aqueous species and gaseous species, but we will not include liquid or solid species. Therefore, the equilibrium constant expression of this equation would be just the concentration of hydrogen multiplied by the concentration of hydroxide ion. That's it, right? We wouldn't divide it by the reactant because the reactant is not aqueous or gaseous. In the previous slide, we discussed what these concentrations are. Remember, each of them is going to be 10 to the negative 7th molarity. Therefore, if you input those numbers, you'll end up with 1 times 10 to the negative 14th molarity. And this is at 25 degrees Celsius. So therefore, Kw, right, the dissociation constant of water, will always be 10 to the negative 14th, given that you're actually dealing with water, right? The water you drink is by no means pure. If it were pure, you would be running into a lot of issues. But if we are talking about pure water, the water dissociation constant will always be 1 times 10 to the negative 14, specifically at 25 degrees Celsius. Because remember, temperature does affect equilibrium. For this reason, if you measure one of the concentrations, you can always calculate the other. For example, if you don't have pure water, you can make implications based on this data. In addition, for this reason, as your hydrogen or hydronium ion concentration increases, the concentration of your hydroxide ion must decrease so the product stays constant, right? Because Kw is a constant. Therefore, if we increase one species, then we have to decrease the other species in order to maintain the value of Kw. So our key takeaways from this initial discussion would be that all aqueous solutions contain both hydrogen or hydronium and hydroxide ions, because remember, when we're talking about aqueous solutions, we're talking about solutions that contain water. Water autoionizes, therefore we will always have these species. Neutral solutions will always have equal concentrations of those two species, right? In other words, for pure water, both concentrations will be 1 times 10 to the negative 7th, and this is molarity. Acidic solutions have a larger hydrogen ion concentration than their hydroxide ion concentration, right? Because hydrogen is going to be what's going to contribute to acidity. Therefore, if we have more hydrogen ions or more hydronium ions in solution, we are going to end up with an acidic solution. But it has to be more than the hydroxide ion, because remember, these can neutralize one another. By that notion, basic solutions will have larger hydroxide ion concentrations than the hydrogen ion concentration. So we've already talked about how to characterize the acidity using the equilibrium constant expression. Now we can talk about how we measure it. We measure acidity using pH. What pH is it's the negative log of the hydrogen ion concentration. Because remember, in acids or in the concept of acidity, we're really talking about what the concentration of hydrogen ion is in solution, right? That's what the acid is dissociating to form. So for example, if you want to determine the pH of pure water, you take the concentration of its hydrogen ions, which remember in pure water at 25 degrees Celsius is 10 to the negative 7th molarity. You take the negative log of that, and that would give you the pH, right? So the pH of pure water at 25 degrees Celsius will be 7. Based on the nature of this equation, right, because we're dealing with log, the scale indicates that anything that's less than 7 is going to be acidic, right, or more acidic. And anything that has a pH of greater than 7 is going to be less acidic or basic. This leaves us with the 7 region, right, which we are going to be indicating as neutral. Remember, the pH of water is neutral, and that's why water has a pH, or pure water has a pH of 7. On the side here, we have some examples of the pH of common items that you're probably familiar with. Things like gastric juice, right? So the solution that you're stomach generates, right, that has a pH of around 1 to 3. Therefore, that substance is going to be considered to be pretty acidic, right? Whereas something like egg whites or milk of magnesia are going to have pHs ranging from 7.6 to 10.5. Those are going to be less acidic or basic. Now, if you're given pH and you want to determine the hydrogen ion concentration, you would still use this equation. However, you'd have to rearrange it to allow for that value to be solved for. Unfortunately, you cannot divide both sides by log. That's not how that operator works. So what you would do, you would take 10 and you'd raise it to the power of both sides, and that would help you get rid of that log operator and isolate the hydrogen ion concentration. I wouldn't recommend memorizing this equation, as it is something that can be simply derived from the first one. Again, pH based on the concentration and based on the negative log operator is going to give us a scale between 0 and 14. So you're not going to end up with a compound that has a pH of more than 14 or less than 0. And because it's a negative log, the lower the number, the more acidic the compound. And the higher the number, the less acidic the compound. This is going to be considered our normal range. pH of 0, think about what the equation is, right? The equation is negative log of hydrogen ion concentration. So if we have a pH of 0, that means our hydrogen ion concentration is 1. So if you ever have 1 molarity, right, or 1 mole per liter of an acid, your pH will be 0, as far as you can go in the normal range. Whereas if you have a pH of 14, right, that would indicate that your POH is going to be 1 molarity. POH is a concept we will talk about shortly. So if pH is the negative log of the hydrogen ion concentration, the POH is going to be the negative log of the hydroxide ion concentration. Nothing's different in using this equation. The only thing that changes is that we're dealing with hydroxide and not hydrogen. Therefore, if you want to determine the POH of a compound, for example, water, you take the concentration of hydroxide, right, which for pure water is 10 to the negative 7th molarity at 25 degrees Celsius. You take the negative log of that, and that would give you its POH. For this reason, anything that's going to have a POH of less than 7 is going to be considered more basic, right, because we're talking about POH now. Anything that has a POH greater than 7 is going to be considered less basic or more acidic. And anything with a POH equal to 7, just like with a pH equal to 7, is going to be considered neutral. From these two ways of measuring acidity and basicity, we come upon this relationship, which we'll discuss in the following slide. So one relationship that we get from these two, operators would be pH of any compound plus its POH will equal 14 at 25 degrees Celsius. And this is proven using the following, theorem. So we already know that Kw, based on the autoionization of water, is going to be equal to the concentration of hydronium multiplied by the concentration of hydroxide. This is equal to 1 times 10 to the negative 14th. Why? Because remember, the hydrogen ion concentration of pure water at 25 degrees Celsius as well as the hydroxide ion concentration of pure water at 25 degrees Celsius are always going to be 10 to the negative 7th. Therefore, when you multiply those two values by each other, you get 1 times 10 to the negative 14th. Now, if you take the log of both sides, right, the negative log of hydronium, right, is going to give you pH, and the negative log of hydroxide is going to give you POH, and the negative log of 10 to the power of negative 14 is going to give you 14. Therefore, based on the autoionization of water, the pH plus the POH of any substance is always going to be equal to 14 at 25 degrees Celsius, because remember, the concentrations that we discussed and the relationships that we discussed regarding the autoionization of water takes place at this temperature. So from this, we can also get a pK, right? So by now, you probably know that a lowercase p indicates the negative log of a value, right? Because pH is the negative log of H, pOH is the negative log of OH, right? So therefore, pK is going to be the negative log of K. In this case, we have a Ka and we have a Kb. Remember, these are the acid or base dissociation constants or ionization constants. pK is going to be the way we will express the strength of an acid or a base on the log scale, right? Because remember, the acid and base dissociation constants are how we are going to measure acidity and basicity. To measure them using a log scale, we take their negative logs. Those would give us these values that we can use to compare the two. So remember, the larger the Ka, the stronger the acid. However, the smaller the pKa, the stronger the acid as well. Because remember, these are inversely related. The same goes for bases. If you have a large Kb, remember that means that you have a lot of hydroxide ions. You have a bigger number in the numerator. However, if you have a bigger number in the numerator, your pKb will be smaller.